Our next team is from the University of Miami, the Water Boys. Their project is on oxygen balance analysis and potential remediation of the upper Almendares River via georelational data techniques. If you guys could speak up on the mic, I want to make sure that everybody's able to hear your presentation, and also we're recording it. So make sure you pull the mic up to your mouth.
It's fine. Thank you. Do we have the printer? Everything works? That's it? Yes. That's right.
Good morning, everyone. Today we're going to present our project, Oxygen Balance Analysis and Remediation of the Upper Almendares River via georelational methods. Our team.
My name is Eric Antman. I'm working on a bachelor's degree in environmental engineering and a master's degree in, my apologies. My name is Eric Antman, and I am working on a bachelor's degree in environmental engineering and a master's degree in civil engineering here at the University of Miami. And I come from the enterprising city of Fort Lauderdale, Florida.
Hello, everyone. Good morning. My name is Miguel Amezcua, and I'm currently working on my bachelor's in civil engineering and architectural engineering at the University of Miami, and I am from Havana, Cuba.
Good morning, everyone. My name is Sergio Claure. I'm in third year undergrad studying civil engineering, and I'm from the mountains of La Paz, Bolivia.
And I'm Leonard Barrera Allen. I'm from Panama, Republic of Panama, and I'm working on my Bachelor's of Science in Civil Engineering at the University of Miami. All right, so let's start with our agenda. First, I'm going to give us the site introduction, followed by the methods portrayed by Eric and Miguel, and finally our conclusion and remediation by Sergio. Okay, so some background information. Here we have a beautiful picture of Cuba. While the climate of Cuba might be somewhat similar to South Florida, the actual topographic relief is very different. There's a lot of mountainous areas, which makes it a different ballgame to what we have in Florida. There's many watersheds associated with Cuba. Mainly we picked the Almendares Vento watershed, but there's also a Cojimar watershed. So the reason why we picked the Almendares Vento watershed is because there's 2.1 million people in Havana, and 47% of the population gets their water from the Vento aquifer, which is located within this watershed. So that makes it an important location to analyze because it is sensible to contamination. So what we have here is a delineation of the Almendares Vento watershed, which is this total area delineated to here, which is about 402 kilometers squared. And within this watershed, we have the Almendares River, which runs from east to west for about 50 kilometers. Now, what you see here is in the white outline is the Ejército Rebelde Reservoir, which is hydraulically linked to the aquifer. And what happens is if the Almendares River has been shown to have point sources of contamination. So if the contaminants feed directly into the reservoir, that will be a direct threat to the public health of the population of Havana. So we need to assess that. Our objectives is to assess the water quality of the upper Almendares River, which feeds into the reservoir, to develop and apply a georelational tool, model the impact of this contamination, and finally evaluate and propose some remediations. Now the methods will be presented by Eric.
Thank you very much, Leonard. Whenever we want to carry out a hydrologic analysis of an area, there are two main factors that we need to be worried about. First would be the topography, the volume of water, where the water is going to fall from the atmosphere as precipitation, and where the water is ultimately going to flow. The second item that we need to consider would be the nature of the contamination. What are the contaminants? Where is the contamination coming from? How is the contamination interacting with our environment? And finally, where is the contamination going to end up? So to address the first topic, the topography, as one of our hosts said, put very simply, there is no reliable source of survey-level information on the Cuban topography. And this obviously presents quite some problems when we want to determine the watersheds and where our water is going to wind up. So our solution was to use a spaceborne LiDAR data through the NASA ASTER program, or the Advanced Spaceborne Thermal Emission and Reflectivity Radiometer. This instrument was flown on the space shuttle back in 1999 and collected a global digital elevation model. The way that LiDAR data collection works is really quite simple. We start out here with the Earth. We have Cuba over there for reference. And then we have a spacecraft. And the spacecraft beams light down to the Earth and looks at the reflected beam of light that comes back from the Earth. By using a sophisticated computer algorithm, the spacecraft can then determine the elevation of the Earth where that beam of light is fired to a very high degree of precision. In this case, give or take 15 centimeters vertically. The trouble is, this is the raw data that comes from our spacecraft. In this form, the data really isn't very useful. We can see more or less that's Havana Harbor, that's the ocean, we have some mountains here, but this isn't very useful. Fortunately, the University of Miami is a site license holder for a software package called ArcGIS, which is an industry-standard georelational data management tool. So we're able to come up with something like this. This is a topographical map that you all should be familiar with. It looks just like any topographical map that may be collected by a survey. The only difference is when we zoom in, you can see these pixels right here. Those square features each represent one burst of light that was fired by our spacecraft, reflected back from the Earth, and then the elevation was measured. These cells are each 30 meters square, so we achieve a relatively high degree of precision, considering that we're taking these measurements from an instrument about the size of this table that's 300 miles above our head as we speak. And what we then did was we connected the high points. These represent the boundaries of our watershed areas. Essentially, a drop of water that falls anywhere within one of these polygons is ultimately going to flow to the same point. It may take a very complex route while it's in those polygons, but ultimately, at the end of the day, it will either evaporate or go to the same pour point. Using the same methods, I can connect all of the low points. These would be the streamlines. So a drop of water falling anywhere in these polygons will ultimately flow to one of the streamlines and then flow to a pour point. As you see on our poster for your reference, we divided the Almendares watershed into an upper and a lower region, which we're going to keep there for your reference. Everything in the upper region in red flows into the reservoir right there, and then into the lower Almendares watershed, where it's joined by precipitation that falls in that area. And what's good about this model is, this model we developed, while we're only talking about a small area in the Havana province, is ultimately applicable to the entirety of the Cuban island, because we have a global data source. So here we have the streams. Right there is the reservoir that Leonard mentioned earlier. And for these streams, our model determined a relative unit flow based on the amount of data flowing into it. Using given information from the flow downstream from one of our sources, we were able to come up with a unit flow value and thus determine an estimate for the dry condition flow through each of these streams. Something you should notice is this looks like a lot of streams for a relatively small area. That's because some of these streams are intermittent. They flow when there is a high flow condition, but during drier conditions, not all of these streams are flowing. Miguel did some further research on the actual flows through these streams that we're going to go into now.
Hello. One of the challenges of assessing the water quality of the Upper Amezcua River is that we do not have water samples. However, we do have access to studies by universities in Cuba and Mexico that have been done on the water quality in the river. These studies use dissolved oxygen as a proxy in order to determine the water quality of the river. Now, dissolved oxygen is affected by the biochemical oxygen demand in the water. the biochemical oxygen demand in the water is a measure of how much oxygen the waste in the water will consume. This consumption can be normally modeled, and you can determine the relative dissolved oxygen concentration anywhere in the river. Now, and we also selected to use this proxy dissolved oxygen in our study. Three main sources of pollution were identified in the upper Almendares River. The first being the city of Cotorro, with a population of 70,000 people, which currently does not have a wastewater treatment plant. This means that all the raw sewage that is dumped into the upper Almendares watershed is not treated, and this raw sewage is high in organic matter, which means it's typically high in microorganisms, which can cause diseases like hepatitis, typhoid, and many other waterborne diseases. The second being the steel mill Antillana de Acero, which also releases untreated effluent into the upper Almendares watershed. And the third being the beer factory Atuey. These 3 point sources release their effluent into the San Francisco tributaries, which later carries the waste down to the Almendares River and then to the Ejército Reverde Reservoir. Like Leonard mentioned before, these waste, it can percolate and leach into the aquifer through the Ejército Reverde Reservoir or through the Almendares River because they are hydraulically linked. Now, using Eric's LiDAR data, we were able to determine base flows, and then we were able to identify 5 mix locations where these effluents and wastewater discharges are discharged into the upper Almendares watershed. The first being mix location 1, which is where the city of Cotorro and the steel factory Antillana de Acero release their effluent into the San Francisco tributary number 1. The second being where the beer factory Atuey releases its effluent into the San Francisco tributary number 2. Mix location 3 is where mix location 1 and 2 mix and later carry it down to mix location 4, which is where the Almendares River meets the tributaries. Then this is carried 2 kilometers downstream and finally empties into the Ejército Reverde Reservoir. Now, in order to determine the flows from each of these point sources, it was very difficult because they do not release the information. In order to do this, we used industry standards and studies that have been done by universities in Cuba, Mexico, and the United States and India. Once we obtained these values through estimation, then we were able to input them into a mass balance in order to model the dissolved oxygen. The dissolved oxygen was modeled by using the initial base flows obtained from Eric's data and then inputting the inputs that we estimated from each point source. And later, using a weighted average, we were able to determine the relative biological, chemical demand and dissolved oxygen concentration downstream of the river. Using the dissolved oxygen concentration values obtained, then we are able to model the relative water quality downstream of the point sources. And now Sergio will speak about the final results.
Thank you. So as Miguel presented, we can use these paired with some key assumptions about the contaminants, and we can model the dissolved oxygen. Once we model this, we can see that at mix location number 1, where the tributary and the steel mill intersect or they join, the DO level in the water decreases immediately until it eventually reaches value of 0, which initially means that the water is already dead at that point, and we're not even in the Almendares River yet. At mix location number 4, where the Almendares River joins these tributaries, there's much more dilution given the flow of the river. And we can see that the dissolved oxygen content spikes up temporarily, and then it eventually goes back down to 0. We've got dead water again. And finally, at mix location number 5, when one last tributary reaches the river, there is a momentary increase in the dissolved oxygen content. And by the time it reaches the Ejército Reverde Reservoir, it's back to 0. It's dead water. We're dumping waste into the reservoir. And if we compare this to the Florida surface standards for class 3 waters, which are for fish and wildlife, we can see the big gap. We see a problem that we have to fix. You know, this is water. No fish can live in it. It's definitely not healthy for humans, whoever come into contact with this. So our remedies, it's a three-step process. The first step process is once we identified our 3 point sources of contamination, we gather all of their effluent together in one point, send it to the Kotoro wastewater treatment plant, which is currently offline. There, it would be provided with primary and a high level of secondary treatment, and we would remove about 8%, 85% of the BOD in the water. This water would finally be pumped to the San Pedro pump station, where it would be diverted into the Kohima watershed, which is much less sensitive to this water and less hydraulically linked than our current Upper Almendares watershed. Finally, once we model these values in our model, we can see that the initial level of dissolved oxygen is already much higher. It does decrease with the time and mix location number 1, but it keeps coming back up, coming back down, but it keeps coming back up. And finally, the most important thing is if we compare it to our class 3 standards, is that by the time we reach the Ejército Rebelde reservoir, although for a portion of the trajectory, the DO level is underneath these standards, by the time it reaches the reservoir, it is above the standards, it is satisfactory, and it can help the fish and the wildlife thrive in this ecosystem and not have adverse effects on the people that get water from this water source in Havana. And finally, when we began this project, we set ourselves some objectives, and if we look back at them, we're able to see that we were able to correctly assess the water quality in the Upper Almendares River using dissolved oxygen as a proxy, and we also can see that the effects of the pollutants with the biochemical oxygen demand lower the dissolved oxygen content. We were able to develop and apply a georelational tool to study this. As Eric mentioned, the transferability of this process is the most important. We can apply it everywhere in the island. We were able to model the impact of the contamination, and it was satisfactory because by the time the water reached the Ejército Rebelde reservoir, after our suggested treatment, it was of satisfactory level. And finally, our remediation program was correctly developed and evaluated. And one last thing, it's a local solution, but it's a nationwide tool. Thank you.